Hello everyone, this is our session 4 on trigonometric functions. We were doing exercise 3.1. We had finished around 5 questions of that. I'll solve one question each of 6 and 7 and then we'll go to the next topic of this chapter. So let us begin. Exercise 3.1, question 6, the first one.
Yes, so exercise 3.1, question 6, we are doing the first one. Okay, so the first question says, find the generalized solution for 4 cos square theta equal to 3. Right, so we have cos square theta is equal to 3 by 4. Okay, this also means that cos theta is root 3 by 2. That means cos square of pi by 6 is equal to 3 by 4, correct? So what is our alpha value? It is pi by 6, okay? So now we have to write the general solution for square angles, that is cos square theta equal to cos square alpha, okay? And its generalized solution, theta is equal to n pi plus minus alpha, okay? So how will we write it for cos square pi by 6? Okay, theta should lie between n pi plus minus pi by 6, okay, and n belongs to z, right? So we have this as a generalized solution for a square value. Remember, square values have a different generalized solution than your regular functions of trigonometry. Okay, let us begin with question 7, the first one. Question 7, we'll take up the second one. So second one is tan cube theta equal to 3 tan theta. Tan cube theta is equal to 3 tan theta, right? So we'll solve this as tan cube theta minus 3 tan theta is equal to 0, okay? We'll take tan theta common over here and we'll get tan square theta minus 3 equal to 0. So now this can be written as tan theta is equal to 0 or tan square theta minus 3 is equal to 0. This will be a square function, tan square theta equal to 3. For a square function, how do we solve it? Find the theta original angle. That will be tan theta for root 3. Now, what is tan theta for root 3? It is tan of pi by 6. So, we write this as tan square pi by 6 is equal to 3. So, your alpha angle will either be pi by 6 or when is tan theta equal to 0? So, we had done these relations wherein tan theta, cos theta and sin theta will be 0 for particular angles. So for tan theta, when is it 0? When theta is equal to n pi. So when theta is equal to n pi, tan theta is equal to 0, right? And otherwise, theta has to be pi by 6 for the answer to be 3. So how will we write the generalized solution? We'll write n pi, or we can write it as n pi plus minus pi by 6, okay, where n belongs to z. For a square function of tan, the generalized solution is given by n pi plus minus alpha. Your alpha is pi by 6 or alpha is n pi, okay. So this is the generalized solution for question 7, second one. Now let us begin with the next part of this chapter, okay. It says solution of triangles. Now, solution of triangles means what? First, we will understand what are polar coordinates. Okay, so we'll go on to a fresh page. Let's check polar coordinates. From polar coordinates, what we can recall is r comma theta is called as a polar coordinate. Let us say there's a point P, then r comma theta is called its polar coordinate. Now, what does this mean? Okay. So let us draw a ray, calling it O, okay, O as the pole point of your circular or radial system. Okay, O as the pole point. Okay, this we call as OX, and this is the fixed ray. Okay, fixed ray OX. Okay, then we draw a vector called as OP, making a small angle theta with OX. Okay, the length of OP is R. Okay, OP is also called as the vectorial ray. Okay, or OP can also be said as the radius vector. Okay, and theta here is called as the vectorial angle or vector angle. Okay, so we have OP as the radius vector and theta as the vectorial angle. That means vector OP is making an angle theta with the fixed ray OX. Then the coordinates of point P, okay, the coordinates of point P are given by r comma theta, where r again is your radius vector and theta here is your angle made with the fixed ray. Okay, now what should we know about theta? So theta is the smallest, okay, smallest non-positive, non-negative, sorry, non-negative, okay, angle made by OP with the fixed ray OX. All right. So what do we know about theta? It is positive, smallest, and made by the vector ray, that is vector r, with the fixed ray, that is OX. Okay, so we have this as 0 less than theta less than 2 pi. So theta should lie between 0 and 2 pi. Okay, now 0, that is the pole point, that is O point over here. Okay, this pole point has no polar coordinates. We have to remember this. The O point has no polar coordinates. Okay, it's just the fixed point, center point, which we call as pole. It has no polar coordinates. Okay, now we'll check with relation between Cartesian and polar coordinates. Right? So let us check this. Now, what is the relation between Cartesian and polar coordinates? So we'll draw our xy axis now. Okay. This as the point A. Okay. This as your x and this as your y. Okay. Then we draw this vector that we need, r. Okay. Yes. And we call this as point P. Okay, with coordinates x comma y. This is making an angle with ax as theta. Okay, and we draw perpendiculars from here. Okay, so this will be distance y, and this is your distance x. This is radius r. Okay, so what we have to find is the relation between the polar coordinates r comma theta, okay, which is that p r comma theta, and between p x comma y. Right? That means if one of them is given to us, we should be able to find the other one. Okay, so let us start from this triangle. What can we say? This is your 90-degree angle over here. Then we can write it as r square is equal to x square plus y square. This is by Pythagoras theorem, right? Also, cos of theta. Okay, cos of theta is adjacent upon hypotenuse, so x upon r. Therefore, x is equal to r cos theta. Similarly, okay, sin theta is equal to y upon r, right? So we can say that y is equal to r sin theta, correct? So what is the relation between the polar coordinates and the Cartesian coordinates? Okay, x is equal to r sin theta, sorry, r cos theta. See, x is equal to r cos theta and y is equal to r sin theta. Okay, so we have this as a relation between the polar and the Cartesian coordinate system. Now, for example, if they give us the polar coordinates of any point, say p 2 comma pi by 4 are the polar coordinates, find their Cartesian coordinates. Right? So find the Cartesian coordinates. So how will we find it? So this is r and this is your theta value. X is equal to r cos theta, right? So we'll have 2 cos of pi by 4, which is x is equal to 2 upon root 2. Let's rationalize this. So we'll get the answer as root 2. And y is equal to r sin theta, which is equal to 2 sine of pi by 4, which will also be equal to root 2. So x comma y is root 2 comma root 2 for polar coordinates 2 comma pi by 4. Okay, I hope polar coordinates and Cartesian coordinates relationship is simple. Let's go to the next topic now. It's called as the sine rule. Okay. Now, before understanding sine rule, we have to know something about a triangle. So let us take a triangle ABC. Okay. So now if this triangle is A, B, and C, okay. So it has three elements, there are six elements, three sides, three angles, right? We call the opposite sides with the small letters. That is, the side opposite to angle A is small a, side opposite to angle B is small b, and side opposite to angle C is small c. Right? So these are the sides of the triangle, and capital ABC are the angles. Now, amongst these, if any three elements are known, then the other three elements of the triangle can be found out. Okay, but the necessary condition here is that the side, any one side also has to be known. That means two angles one side, two sides one angle, or all the three sides. Okay, so necessary condition is amongst the three elements that we know, one of the sides should be known. Okay, then we can find the other elements of the triangle. Now we have some rules to find out these other elements. So what are these rules? First one is called as the sine rule. Okay, so let us begin with the sine rule. Now how is the sine rule stated? A upon sine A is equal to B upon sine B is equal to C upon sine C, okay, is equal to 2r. Now what is 2r over here? R is the radius of, R is the circumradius, you can say, okay, radius of the circumcircle. So circumradius of triangle ABC. Yes, so R is the circumradius of triangle ABC. The sine rule says A upon sine of capital A, B upon sine of capital B, and C upon sine of capital C are equal to each other, as is equal to 2R. We have to prove this, so let us begin with the proof over here. To prove that, we'll put in first A upon sine A is equal to B upon sine B. is equal to C upon sine C equal to 2R, right? We require the diagram for it, so we'll put in the diagram first. Should have the triangle, right? So just, okay. And we are going to do a construction here, so I'll write the construction first. Okay, construction is draw AD perpendicular to BC. Okay, so this is AD. This is AD perpendicular to BC. Okay, and we'll name the opposite side. This will be B, C, and A. And this is here 90 degrees. Okay, how do we start the proof now? So for the proof, sine C is equal to, first step, sine C is equal to, what is sine C in the diagram? Can we see? Sine C is AD upon, opposite upon hypotenuse, that is B. AD upon B. Okay. Then second step, area triangle ABC is equal to half into base into height. What is the base of the triangle? BC, right? And height is AD, right? So we'll have half into, what is BC in small letters? It is small a, okay? And AD will be B sine C. So B sine C from 1. Okay, this is half AB sine C. So we can write this as 2 area triangle ABC is equal to AB sine C. Okay, this is our third step. Let's go to the next step, fourth one. Okay, similarly, we can have 2 area triangle ABC is equal to AC sine B, and we can have 2 area triangle ABC equal to AB sine C, AC sine B, BC sine A. In similar manner, we'll draw perpendiculars on each one and find the remaining angle. Okay, so this will give us 3 ratios for the area of the triangle. So we can say from 3 and 4, we can equate them. From 3 and 4, we can write AB sine C equal to BC sine A equal to AC sine B, right? Okay, now what we'll do is divide the entire ratio over here by ABC. Okay, so we'll say divide throughout by ABC. Divide throughout by small ABC. BC. Okay, so we have AB sine C upon ABC equal to BC sine A upon ABC equal to AC sine B upon ABC, correct? So we'll have AC cancelled here, we'll have BC and we'll have AB. So we'll have sine C upon C, okay, we'll have sine C upon C equal to sine B upon B equal to sine A upon A, okay. We'll just invert this ratio by invert endo, and we can say A upon sin A is equal to B upon sin B is equal to C upon sin C. Okay, and we'll call this as equation 1. Okay, now we'll prove the other half, that is radius 2r. Okay, now what is 2r? It is called as circumradius, right? So how will we prove that? We require a circumcircle across our triangle, around our triangle. So how we are going to put that? Let's make the circumcircle first. Okay, we have the circumcircle. Now we'll put in the triangle into it. So we'll have this. Okay, and the third line over here. Yeah, so this is your triangle ABC. Let's name it. This will be A, B, and C. Okay. Now this is small b, this is small c, and this is small a. Okay. Now we are going to draw the diameter of this circle. Okay, starting from A. So we start from A and we draw the diameter of this circle. So that is your construction over here. Now why are we doing this construction? So there are three angles in triangle ABC. Their addition is 180 degrees, right? So we have angle A plus angle B plus angle C equal to 180 degrees. So any one of the angles is less than 90 degrees, correct? So I'm considering let A be, or let A not be 90 degrees. Okay. So from A, I'm dropping a diameter which is passing your center O over here, okay, of the circumcircle. So what will be, let's say we'll call this AD. What will AD be? It will be 2R, right? Have we named D previously? Let me check. Yes, we have named it. So what we'll do is we'll name this as P over here. Just a minute. Yes, we call this P. Okay, AP is equal to 2R, correct? Because we are calling it as the diameter of the circumcircle. So it will be AP is equal to 2R, right? Now I'm joining P to C. Let's use a scale. So we have P to C joint. Yeah. Now, what is the angle ACP equal to? Angle ACP, okay, is an angle inscribed in a semicircle or angle subtended by a diameter. So angle ACP is equal to 90 degrees. So this will be 90 degrees, correct? Okay. Now from here, also one more thing we can understand is angle APC is equal to angle ABC. Why? Because they are inscribed in the same angle. Sorry, inscribed in the same arc. Inscribed in the same arc. Right? So if they are inscribed in the same arc, then their values are equal. So we can write that sine of P is equal to sine of B. Okay, which is equal to, now what is sine of P? It is opposite upon hypotenuse in triangle ACP. Okay, so we can write this separately as well. In triangle APC, in triangle APC, angle ACP equal to 90 degrees. Okay, therefore sine of angle APC Name the triangle wrong. Yeah. Sine APC. Now, what is sine APC from the triangle? It is opposite upon hypotenuse b upon 2r. B upon 2r. So, therefore, sine P equal to sine B is equal to b upon 2r. Right? Therefore, sine, or we can say b upon sine B is equal to 2r. Correct? This we call equation 2. And then we say from equation 1 and equation 2, we can write that a upon sine A is equal to b upon sine B is equal to c upon sine C equal to 2r. Right? Any one angle you have to prove equal to 2r, that is any one ratio, that is like I've proved b upon sine B as 2r. Okay. Same thing you can repeat if you want to drop a diameter from B to the opposite end and then prove for sine of angle C, sine C. Okay, so that could be possible as well. So similarly, we'll get the three ratios, and that is why all the three ratios are equal to 2 times r. R is the circumradius or radius of the circumcircle. Okay, this is your proof for the sine rule. Sine rule can be written in multiple ways. I will just specify those ways. This is the basic way of writing the sine rule. Then we can have, let's say if this is our first one, then second one could be A is equal to 2r sine A, just cross multiplying. B is equal to 2r sine B. C is equal to 2r sine C. What else combinations can we make? So let's take the third type in which we can write it as, we can write sine A upon A is equal to sine B upon B is equal to sine C upon C, okay, equal to K. We can, since they are ratios, we can equate it to K as well. Okay. Then we can have one more method. We can say B sine A is equal to A sine B. Right? First two ratios. Then we can say B sine C is equal to C sine B. And the last one could be A sine C equal to C sine A. Just cross multiplying various ratios, various combinations, you can get different types of the sine rule. The last one, fifth one, A upon B. Now I'm taking different ratios. So A upon B will be sine A upon sine B. Okay. B upon C, just go by the letters. So we can say sine B upon sine C. Very easy to remember. A upon C is equal to sine A upon sine C. Basically, letter and angle go together. So even when you're writing the sine rule, the side A upon this angle sine A, the side B upon the angle sine B, and the side C upon the angle sine C. Okay, so we can relate letter to the angle. This is your sine rule in 5 different ways. Okay. Now, this is our end to the sine rule. We have to go to the cosine rule, projection rule, and then we can start with the next exercise. If you have any doubts in the sine rule or the previous exercise, do write to me. I'll solve and send it to you. And if you have a doubt in the sine rule also, please tell me about it. Thank you so much.